In this module, you will learn about Thomson's atomic model. Are the charged particles arranged in any particular manner? Are the charged particles spread throughout the atom, or are they concentrated in one place? To answer these questions, let's go back in time. Dalton's atomic theory stated that an atom was indivisible and indestructible. However, in 1886, Goldstein came upon positively charged radiations in a gas discharge, which he termed as canal rays. These radiations led to the discovery of the proton. The mass of a proton was about 2,000 times that of an electron, and it carried a positive charge. Around the year 1900, J. Thomson conducted experiments on the beams of particles inside a glass tube called a cathode ray tube. He found that the particles were attracted to the positive terminal of the tube. Thomson concluded that the particles must be negatively charged and called these particles electrons. An electron has a negligible mass and has a charge of -1. These discoveries made the scientists believe that an atom was divisible and made up of electrons and protons. What they didn't know at the time was how these electrons and protons were arranged within an atom. They tried to understand this arrangement through various experiments. J. Thomson was the first to put forward a model to explain the structure of an atom. In his model, Thomson compared an atom to a Christmas pudding. The electrons were like the raisins in the pudding, and the pudding itself was like the positively charged particles. This can also be explained through the example of a watermelon. The positive charge in the atom is spread all over like the red, fleshy part of the watermelon, while the electrons are embedded into the atoms like the seeds of the watermelon. The oppositely charged particles are held together by electrical force of attraction. Thomson concluded that an atom consists of a positively charged sphere with electrons set within the sphere. An atom is electrically neutral as the positive and negative charges within it are equal. As per Thomson's conclusion, the electrons were embedded in a sphere of positive charge. This conclusion, however, was incorrect. Thomson asserted that the positive charge spread through the atom held the negatively charged electrons due to electrical forces. This assertion failed to explain many experimental observations. In this module, you have learnt that atoms are made of charged particles. According to Thomson's model, an atom is a positively charged sphere with electrons set within it. An atom is electrically neutral. Shortcomings of Thomson's model are his incorrect assumptions. Electrons are embedded in positive charge. Positive charge in the atom holds the negatively charged electrons.
Rutherford's model of an atom. In this module, you will learn about Rutherford's model of an atom. A number of scientists worked on the structure of an atom. One of the first scientists was Sir J. Thomson, but his model could not explain the results of several experiments. One of those experiments which could not justify the Thomson model was done by Rutherford. Rutherford's experiment got popular by the name of alpha particle scattering experiment. To understand about his experiment, let us first see what alpha particles are. Alpha particles are emitted by radioactive substances. These are helium ions with double positive charge. Now let us look into the details of the alpha particle scattering experiment. The setup of the experiment consisted of a thick lead box with a hole on one of its walls, a slit, a thin gold foil, and a rotating detector at the end. Inside the lead box, a radioactive substance rich in alpha particles was kept. Now, let us see the experiment. Alpha particles emitted from the radioactive source passed through the hole and entered into the slit to get streamlined. The thin streams of the particles then bombarded the gold foil and got scattered in different directions. Their scattering pattern was shown by the detector. It was expected from the Thomson model that it should show a large number of deflections. But something else was observed actually. The detector showed that most of the alpha particles passed through the gold foil as such without showing any deflection. Only a few of them showed deflection in different directions. A very few of them, essentially 1 in 12,000, rebounded back. Such observations led to significant conclusions. Let us see what those were. As most of the particles passed undeflected, Rutherford concluded that most of the space inside a gold atom was empty. A few particles were deflected from their path by small angles, indicating that there must be a positively charged center, which was repelling alpha particles. As these particles were few in number, this led to the conclusion that a positively charged center occupies a tiny space. The few particles that are rebounded back indicate that all the positive charge of the atom was concentrated in a very small volume in the center. Rutherford named this positive center of the atom as a nucleus. Looking at the proportion of the particles undeflected, deflected, and rebounded, and based upon some calculations, Rutherford concluded that most of the mass of an atom is concentrated in its nucleus. Based on all these conclusions, Rutherford suggested an atomic model, which was known as the nuclear model of atom. According to Rutherford's nuclear model, there is a positively charged center in an atom called nucleus, and all the mass of the atom is due to this nucleus. It also suggested that electrons of the atom revolve around its nucleus. This model was also known as planetary model, as the nucleus of the atom can be compared to a miniature sun, and electrons revolving around the nucleus can be compared to the planets revolving around the sun. But this model did not get much acceptance, as it said that the electron keeps revolving around the nucleus. However, later it was found that any charged body while moving in a circular motion undergoes acceleration. On undergoing acceleration, it should use some energy. So the energy of the electrons should keep decreasing. As a result, the path in which the electron is moving should keep becoming smaller, and thus, finally, it should fall into the nucleus, and hence the atom should collapse. So, the nuclear model could not explain the stability of the atom, and this was its major drawback. Let's recap. Rutherford gave a nuclear model of an atom which was based on his alpha particle scattering experiment. According to the Rutherford's model of an atom, all the positive charge and mass of an atom is concentrated at the center. The center of an atom is called the nucleus. The size of the nucleus is very small as compared to the size of the atom. The electrons of an atom revolve around the nucleus. The major drawback of this model was that it could not explain the stability of the atom.
Ernest Rutherford had given his structure of atom, known as the Rutherford's model of atom, in which he explained that most of the space in an atom is empty, the entire mass and the positive charge is concentrated in the center of the atom, known as nucleus, and the electrons revolve around the nucleus in this empty space. One of his students was Niels Bohr. He was extremely interested to study the structure of atom. But later on, when he saw the Rutherford's model, he was not convinced. Because according to the laws of physics, if a charged body is in motion, it radiates energy. So if electron, which is negatively charged, it is moving around the nucleus, it continuously loses energy. And therefore, it moves closer and closer to the nucleus. And hence, it should collide with the nucleus. So Rutherford's model was not able to explain the stability of the atom. When Bohr told this to Rutherford, he appreciated his student's work and asked him to study the structure further. So Niels Bohr, a brilliant scientist, gave his atomic model in 1913. Let's see how he explained his model. So according to Niels Bohr's model, the electrons revolve around the nucleus in definite orbits. They revolve in these definite orbits in which they do not radiate energy. So only particular orbits are these paths in which the electrons revolve. So only particular orbits are allowed in which the electrons can revolve without losing energy. So the electrons which are closer to the nucleus, they are attracted towards the nucleus with a greater force, and the electrons which are away from the nucleus in the outer orbits, they are attracted towards the nucleus with a lesser force. And so, if an electron from an orbit closer to the nucleus is to be moved to an outer orbit, it requires energy. So energy is required to move an electron from an orbit which is closer to the nucleus to an orbit which is away from the nucleus. So let's see the points given by Bohr again. So according to Bohr, the electrons revolve around the nucleus in certain fixed orbits. He called these orbits KLMN, that is the orbit which is closest to the nucleus. It is the K shell. The orbits are also known as shells. So it is K shell or K orbit. So the second shell or orbit is the L shell, the third is M, N, and so on. He related the energy of these orbits to their size. So the orbit which is closest to the nucleus, it's smallest in size and therefore it has the lowest energy. The second orbit has a little higher energy as compared to the orbit which is closest, and the outermost orbit, being the longest or the largest orbit, has the highest energy. So that is the highest energy orbit. So we have seen that to move an electron from an orbit which is closer to the nucleus to an outermost orbit or an orbit which is away from the nucleus, energy has to be given to the electron. So energy is always absorbed or emitted when an electron moves from one orbit to another. So only when an electron moves in between these orbits that energy is absorbed or emitted. It does not radiate energy on its own. That is, when it is revolving in a particular orbit, it does not radiate energy. Only when it moves from one orbit to another that it absorbs or radiates energy. According to Bohr's model of atom, which orbit has the minimum energy? Bohr had marked his orbits as if this is the nucleus. So the first orbit he had named as the K shell, the second was L, and he related the size of the orbit to their energy. So the smallest orbit, which is closest to the nucleus, has minimum energy. So the orbit which has minimum energy is the K orbit or the K shell. So Rutherford's model was not able to explain the stability of the atom. If the electron, which is negatively charged, is moving around the nucleus, it should constantly radiate energy and should collide with the nucleus. So Rutherford's model was not stable, whereas Bohr was able to explain the stability of the atom. According to his model, the electrons revolve in definite orbits in which they revolve without losing energy. Only when they move in between these orbits that they emit or absorb energy. So Bohr was able to explain the stability of atom. Well, scientists put in a lot of effort to give these results, but not always are the efforts appreciated in the beginning. Niels Bohr initially wanted to be a student of J.J. Thomson. He presented his work to J.J. Thomson, but Thomson was not satisfied with his work. So he refused to accept him as a student. Later on, Bohr was able to give his model, the Bohr's atomic model, which we accept today. So even though scientists face a lot of rejection or criticism in the beginning, they continue to work and at times they give brilliant results.